My name is Louise King, and for those of you who don't know me, I'm part of your minimally invasive gyne surgery department. It's my honor today to introduce our speaker. I'm lucky enough to have this honor because I'm also lucky enough to be friends with Professor Adachi. And so I was tagged and very happy to be tagged to give the introduction. Ellie Adachi is a professor of medical science and the former dean of medicine and biological sciences at Brown University. He's a graduate of Tel Aviv University School of Medicine, I think the first class of graduates there, and a graduate of the public health program here at Harvard. His biography is long and quite impressive and inspiring to me, certainly. I encourage you to take a second to read through it, either on the Brown website or on Wikipedia. Relevant to his talk today, he's an elected member of the National Academy of Medicine and the National Academy of Sciences, and has served and chaired on multiple committees, been a reviewer and coordinator for close to 30 of the NAM reports. I was recently lucky enough to be part of a NAM committee meeting on textiles, and these are these wonderful meetings, if you're not familiar with them. They bring together these incredible experts and think tank through very important problems. And he reminded me this morning that he recently serves as the chair of the in vitro derived human gametes as a reproductive technology workshop that just happened and a publication ensued. And so he'll be giving his talk today on that topic. He's also an example to all of us as mentors to each of you. He's been a mentor to over 50 postdoctoral trainees, including a very important mentor to my husband, Alan Penzias, who many of you know. And a mentor to colleagues that I have at the Harvard Law School as well. So he's just an incredible mentor, bridging interdisciplinary medicine and other areas of interest in a way that very few people can. But being such an incredible mentor and an author of close to 800 peer-reviewed publications, and editor or co-editor of over 16 books, so incredibly prolific. His talk today is titled In Vitro Gametogenesis, Producing Eggs and Sperm from Buccal Smear. And I'm, again, so honored to introduce you today.
Did you hear me all right?
Yes.
Okay. Well, thank you all for joining us this morning. It's a pleasure to be here. As you will see, I have some history with this institution, albeit peripheral. I never was a member of the faculty, but I spent some time in Boston and always been very cognizant of the force that this department constituted. Topic today is really about what will happen tomorrow. And what will happen tomorrow is quite stunning and is really an amazing story that has its origins, I might add, in Japan, and is still being pushed and advanced mostly by Japanese investigators. But it essentially turns reproduction upside down. And not only will it replace IVF in due course, but it will also allow same-sex couples to be the genetic parents of their children. In the case of men, of course, a surrogate will be required to carry that embryo, but nevertheless, the technology is emerging that will make it possible for same-sex couples to be the genetic parents of their children. By way of background, I should say, and that's my Boston background, I did my residency training at Tufts University, and the picture I'm depicting here is a contemporary vision of the New England Medical Center, where I spent 3 years between 1974 and 1977. At that time, as some of you may know, your department was mostly, exclusively, located in the Boston Lying-in Hospital. And because my wife and I were living in Brookline, every so often, I would join on my way to work I would stop at the Boston Lying In Hospital to listen to grand rounds. At the time, of course, the chair of the department was Ken Ryan. The person who organized grand rounds was, in fact, Frederick Naftalin, who eventually became chair of OBGYN at McGill University in Canada and later on at Yale University. So some really important and well-known individuals were running the show. And here I was, a resident, sneaking in, trying to catch grand rounds when I could. Another connection I had to the Boston Lying In Hospital was the birth of my son, which was born here on December the 6th, 1975. The obstetrician being Lenny Saffron, who by now I think only Dr. Kramer probably knows amongst the members of the audience. But Lenny was a great guy and of course a great obstetrician. And I know he was very well liked by the veterans of this department. He passed away in 2004 after retiring to Florida. But today we will speak about in vitro gametogenesis, but we can't do that without recalling its predecessor, if you will, which is of course in vitro fertilization. The acknowledged father of which is Bob Edwards, who in 2010 received the Nobel Prize for Physiology and Medicine for this accomplishment. It is important to note that some of his important co-investigators did not receive the Nobel Prize only because, regrettably, they were no longer alive. It so happens that the Nobel Committee only awards the prizes to living individuals. As it turns out, Bob Edwards at the time was not well or well enough to attend the ceremony in Stockholm. And so it was his wife who ended up traveling to Stockholm to receive the Nobel Prize on his behalf. The beginning of in vitro gametogenesis is a little bit difficult to pinpoint, but I settled on a paper that was published in Cell in 2009 that was titled A Signaling Principle for the Specification of the Germ Cell Lineage in Mice. The senior author, and that will become important, as you can tell, was a certain Mitinori Saito, who was an MD PhD at the University of Kyoto, which is, you could say, the Harvard of Japan and highly regarded school with Nobel Prize winners and the like. Indeed, the two principles that we owe IVG to are Mitinori Saito, who I just mentioned, and Katsuhiko Hayashi, who has at the time worked with Dr. Saito, but eventually branched out on his own and is currently at Kyushu University and publishing truly impressive papers on his own in Nature, Science, and the like. In 2013 or thereabouts, I was in Japan for another reason, but being cognizant of what was happening in Kyoto, I booked a flight to Kyoto and made a point of visiting with these two gentlemen and sitting down with them in the lab and having a long conversation about their work. And it was so impressive that I really never, ever lost interest in this subject, which is only continuing to progress, although it has yet to be fully realized in the human context. As you can imagine, the experimental paradigms have proceeded along two parallel lines. The rodent, which makes obviously all the sense in the world, And the human, which has yet to come to some sort of closure or full realization of the potential of this technology. But to understand IVG, you have to know something about so-called pluripotent stem cells. That is to say, cells that either derive from an embryo, and I will describe that, or are induced in a technology that I will also discuss. But the main point of which is that they can become anything. So stem cells can become any cell type you may wish to imagine. We could, for example, replace missing cells in the retina in individuals who, for example, are lacking the amacrine neurons. We could potentially inject into the striatum dopaminergic neurons in patients who are suffering from Parkinson's, for example. Or we could perhaps develop motor neurons and even overcome paralysis in individuals whose spinal column was interrupted in some fashion. So the potential of pluripotent stem cell is infinite, although it will be a while before that full potential is realized. Now, of course, our discussion today will revolve around stem cell-derived gametes because that is what we do for a living. And so I will obviously focus on that issue, but the technology in principle could be applied in other arenas. Science magazine did not lose sight of this evolution and dedicated a full spread in 2021 to mammalian in vitro gametogenesis, authored by the two principals I just introduced you to. The New England Journal of Medicine, not to be outdone, published in 2022 a paper titled Oocytes from Stem Cells that they commissioned from Mary Herbert and Azim Surani from the UK. And last year, in April, we organized a workshop in Washington, D.C., under the auspices of the National Academy of Medicine, wherein the whole set of issues that are related to in vitro gametogenesis were aired out over a 2.5-day period. And a book was published for those of you who wish to, in fact, read up the summary. I'm also mentioning here, in the context of relevance, the interest of the Nuffield Council on Bioethics in the UK in vitro-derived gametes. As you know, the Nuffield Council on Bioethics is the premier bioethical institute or organization in the UK. They study lots of issues, although they definitely include human reproduction. And when you look at their agenda for the year, in vitro-derived gametes is at the top of the list. Yes, they will talk about time limits on maintaining embryos in culture, womb replacements, preconception screening, whole genome sequencing of embryos and fetuses, genome editing of gametes and embryos, and egg freezing. But at the top of the list is in vitro gametogenesis. That tells us also something about where our colleagues from across the ocean place and prioritize in vitro gametogenesis. I think we can all agree without too much discussion that this constitutes a disruptive technology. Whether or not it's achievable in the human remains to be seen, and I will delve into that a little bit later. And of course, the timeline is still uncertain. But as I look at the young members of the audience who are sitting to my right, I suspect you will be there to see it happen and quite possibly to apply it, given that you are in the reproductive arena. Now, before we go forward, it's always useful to recall a very important historic contribution of Aldous Huxley, who in 1932 wrote the all-important contribution known as Brave New World, wherein he made several predictions, one of which was that eggs will be produced via ex vivo ovarian cultures, not quite in vitro gametogenesis, but close. He also predicted that embryos will be created via in vitro fertilization. And we all know that that was perfectly true and realized in 1978. He also predicted that newborns will be carried and delivered via ex vivo ectogenesis, relieving women, if you will, I'm using this in quotes, relieving women of the burden of carrying a pregnancy for 9 months. Well, we're not quite there yet with ectogenesis, but we do know, of course, that embryos can be created via in vitro fertilization, and that this technology is central to the rectification of infertility. In chapter 1 of Brave New World, the so-called director of hatcheries and conditioning is saying, 1 egg, 1 embryo, 1 adult, normality, making 96 human beings grow where only 1 grew before, progress. Remember, this was conceived in the 30s. And to have this kind of imagination that to those of us who live in the present is not particularly revealing, it is remarkable that he was in fact able to foresee so much at the time that preceded IVF and other developments by many, many years. And by the way, through in vitro gametogenesis, we can, of course, have multiple embryos in 96 well plates, although one could legitimately question the import or the need in having 96 embryos in any type of culture context, but it is now feasible. Now, it wasn't easy going in some respects because there were some theoretical obstacles. We are all probably not young enough or too old to recognize what was known at the time as the soma germline barrier hypothesis, which was the brainchild of August Weismann, professor of zoology at the University of Freiburg, who in his 1893 book, The Germplasm, A Theory of Heredity, maintained what persisted for the longest of time, namely that the germline gives rise to the soma, which is of course true, which then, according to him, is immortal. But that the soma never gives rise to the germline, which is mortal, that is to say the soma, which of course is turned on its head in the context of in vitro gametogenesis. So to launch now into the meat of the in vitro gametogenesis story, perhaps we should say a word about pluripotent stem cell formation and the technologies thereof. The first technology is known as somatic cell nuclear transfer, or SCNT for short, and it was developed in 1958 by John Garden, professor at Cambridge University in the UK, worked with frogs and who published a paper in Nature in 1958, wherein he took the nuclei of somatic cells, injected them into enucleated oocytes, and created quasi-zygotes that developed into blastocysts with an inner cell mass, which could eventually produce embryonic stem cells. That could go anywhere. That could be anything. In 2006, the induction technology was introduced by Shinya Yamanaka from Kyoto University, who started with a somatic cell, injected it with select transcription factors, and produced what is now known as induced pluripotent stem cells. Both individuals earned the Nobel Prize in Physiology and Medicine in 2012. And it is to these two individuals that we owe the advance we refer to as pluripotent stem cells, irrespective of which method you use to create them. Because once you have a pluripotent stem cell, in theory, it can become any type of cell. And in theory, it could be curative to all kinds of maladies that are difficult to imagine. Which brings us back to in vitro gametogenesis, which starts with a somatic cell, involves conversion to an embryonic or induced pluripotent stem cell, and then guiding that stem cell towards a gametogenic fate. And the question is, how does one do that? Well, you need to know all kinds of you need to have all kinds of information to be able to pursue this kind of lofty goal. You have to know the cues that have to be applied to the cell, the sequence by which those cues are applied, the timing thereof, and the presence of a niche. And the reason I say this is because, as you know, oocytes are surrounded by granulosa cells. And sperm are surrounded by Sertoli cells. Those are the so-called, constitute the so-called niche. And you really cannot imagine, or should you, the development of male or female germ cells without those surrounding, sustaining niche cells that engage in crosstalk, which we are still trying to figure out, but which is definitely essential for the maturation of either an egg or a sperm. It's a little hard to pinpoint the beginning of the work in the rest of the world, if you will. Best we can make out a science paper in 2003, which was senior authored by Hans Schürler, who at the time was at the University of Pennsylvania, but is now the director of the Max Planck Institute for Molecular Biomedicine in Germany. He reported on the derivation of oocytes, which are shown on the right lower hand side of the slide, derivation of oocytes from mouse embryonic stem cells. So in many ways, we are inclined to identify this paper as an important start. But that same year, Toshiaki Noche, in a paper in the Proceedings of the National Academy of Science, reported that embryonic stem cells can form germ cells in vitro. And George Daly, presently the dean of your medical school, published in Nature in 2004 a paper titled Derivation of Embryonic Germ Cells and Male Gametes from Embryonic Stem Cells. And Rene Rejo-Pera, who at the time was at UCSF, published a paper in Molecular Genetics titled Spontaneous Differentiation of Germ Cells from Human Embryonic Stem Cells in Vitro. And the beat goes on. You can see that over the next 10 or more years, several relevant papers were published in leading journals as they related to the rodent model on germ cell specification. And more of the same applied to germ cell specification pathways in the human. And so when we try to assess where we stood in 2015, we can say that the germ cell specification pathway, best we could tell at the time, was not conserved between the rodent and the human. And that the genetic network involved are actually quite distinct as well. In a word, we could take an embryonic stem cell or an induced pluripotent stem cell and convert it into a primordial germ cell-like cell. But what we really didn't know how to do is to take that cell and convert it into a haploid post-meiotic mature gamete. In a sense, we mastered the extragonadal component, but we had yet to master its intragonadal counterpart. And so the final frontier, of course, was to achieve in vitro gametogenesis all the way. Back to our old friend, Katsuhiko Hayashi, who now was working on his own and published a paper in Nature titled Reconstitution in Vitro of the entire cycle of the mouse female germline. So he started off with stem cells, combined them with granulosa cells, and produced primary oocytes in the rodent and M2 oocytes, which are shown here, which upon fertilization gave rise to embryos and blastocysts and eventually to pups. So at least in the rodent, he now documented that you could start with a stem cell and end up with pups. This was the first demonstration in the rodent of the feasibility of the process. Given their entrepreneurial spirit, because the granulosa cells that he used were honest to goodness mature granulosa cells, he undertook the challenge of designing and creating granulosa cells as well from stem cells. And so that's sort of a sideline which was published in Science in 2021. And more of the same transpired on the male side, this time by Mitinori Saito. The paper was titled In Vitro Reconstitution of the Whole Male Germ Cell Development from mouse pluripotent stem cells. Now, I hinted at the beginning that the human paradigm wasn't quite as advanced. And this is really where we are today in terms of state of the art. If you combine human primordial germ cell-like cell with somatic cells, Mitinori Saito was able to take those cells all the way to the orgonial stage, but not to the M2 oocyte stage, which is to say that we still have a ways to go to really fully accomplish, if you will, our mission. And much of the same on the human side is true for the male. This paper by Kotaro Sasaki, who is at the University of Pennsylvania, is probably the most advanced example of reconstitution of spermatogonial cells from induced pluripotent stem cells, but again, not all the way. So on the human side, we still have some work to do. We have to get M2 oocytes, and we have to get spermatozoa, which we haven't quite yet accomplished as we speak today. Now, if and when we arrive at that promised land, there is significant scientific and translational promise. For one, it will afford us with an inexhaustible supply of germ cells. It will allow us to do what scientists love to do, so-called functional null-mutant analysis, and ask, what does this gene do? How do you function without it? And we could study germ somatic cell interactions like never before. On the clinical side, we could, for the first time, envision the reversal of germ cell failure by autologous gamete replacement, maybe gene-edited gamete replacement when the genetics is flawed. And as I said, for the first time in human history, allow same-sex parenthood, or that I should say genetic parenthood, of 2 women or 2 men. And as some of you surmised, and as we may have said earlier, this will have an impact on IVF. It will eliminate the need in stimulation and egg retrieval, or so it seems. It will do away with gamete donation, and it will, in effect, convert IVF to a laboratory procedure. You would still need to prepare the endometrium and to transfer the embryo, but all the steps that lead to that point could potentially be bypassed. And in theory, you could improve affordability and thus access, because we all know that IVF is hardly cheap. But I will hasten to add that we've been there before. We've made those predictions before. And somehow, with American ingenuity, finds a way to jack up the price, no matter what the technology may be. And so don't hold your breath is, I think, what I'm saying. Now, as is self-evident, you can't just let loose with such technology without oversight. And so regulation will be essential. And as is appropriate in this case, it will require FDA jurisdiction, specifically by the Center for Biologics Evaluation and Research, or CBER, as it's abbreviated, and is currently headed by Peter Marks, MD, PhD, who is a product of this very program, but who is currently working at the FDA. And they, using their lingo, will assign this application to the so-called human cells, tissues, and products, or in their lingo, HCT/Ps. So even when this technology becomes a reality, it will need FDA adjudication and approval by the FDA branch that we just discussed. Which brings us back full cycle to the NAFLD Council on Bioethics and to the seemingly appropriate placement of in vitro derived gametes at the top of their agenda. Evidently, the desire to come up with gametes to order is very strong, and IVG will definitely, or could definitely, serve that very purpose. And so all I can say today is stay tuned, because there's still some work to do in the human. We still need to cross the regulatory threshold. But once both are accomplished, and again, I point out to the young members of the audience to my right, this could become a reality. And it would definitely simplify IVF. It would definitely make it possible for same-sex couples to be the genetic parents of their children. And I have a separate lecture on pregnancies or successful reproduction in same-sex couples. And so, as is always true in science, in our business, any business, life moves on, new developments arise, new technologies make their presence known. And it will, one way or the other, change reality as we know it today. So hopefully, I have left you with a sense of the future, because we're not there yet. But what you're looking at today is a combination of efforts that began in Japan. I'm estimating around 2005 or so. So we've been at it now for some time. I mentioned to my host that there's actually relatively little activity in the US on this score. Not complete absence, but considering our size, potential, and capabilities, it's actually somewhat surprising that not more is happening on US soil. And so as we speak today, I would say the driving principle remain our Japanese colleagues who started this whole field and are continued to push it forward. The latest contribution from that team came from Katsuhiko Hayashi, published in Nature a month or two ago. He made it very plain that in the rodent, you could take a skin cell from a rodent, convert it to a gamete, and actually produce a pregnancy in a rather impressive fashion. So for now, stay tuned, but it's coming. It's just a matter of time. So thank you very much for your attention.
Are there any questions in the room?
This isn't yet on the radar of social conservatives. Predictably, it will become.
The great.
And could you foresee the Congress saying to NIH, don't fund any research on creating gametes.
Well, it's entirely possible. I'm just as sensitive as you are, Daniel, to some of the conservative elements we always have to deal with. I don't know that this falls directly under the current legal limitation of the NIH, which is obviously already limited in funding human embryo research. But it's a question that really individuals such as Louise and others need to help us with, figure out. Fortunately, I say this in quotation marks, we didn't have to face this question because we're not there yet. First, we need to get to a point where we really produce functional gametes in the human. Then we need to do clinical trials. And then, and only then, can we apply to the NIH for approval. Before that ever happens, I'm sure legal advice will be extensively sought to determine, one, is it even feasible? And two, if it is, what kind of fine points do we need to include in the application? What should we stay away from? What should we say? What should we not say? On and on. Such is life in a pro-choice, pro-life society that we are, for better or worse. And I'm not going to pass judgment. I'm just going to say it's a reality. I think in departments of OBGYN, I think the position of most individuals is clear. But as this very election probably is telling us, it's still a very complicated matter. Yeah.
Yeah, I think that's an astute question because as different conservative states pass further ballot measures like they did in Alabama, which created a constitutional protection of personhood for a state constitutional protection of personhood for the embryo. Research wouldn't be possible in Alabama, but it might be possible nationally. It's interesting.
Oh, that's what Donald Trump wanted. States to decide the issue.
True.
Well,
Any other questions?
it's interesting that Alabama is home to the American Society of
Yeah.
Reproductive Medicine. But as a non-legal person, this would probably not be a very intelligent comment, but on the whole, it's not over until it's over. There could be more litigation, more challenges, possibly Supreme Court involvement, who knows? Point is, we're still some distance away from having to face these challenges.
Okay.
To assume that, you know, our national trends will somehow change or be reversed, I think is probably naive to think. And so the challenges we face today are likely going to be the same challenges we face 10, 20, whenever years from now, we actually have to take this type of technology to the FDA and beyond.
I don't see any questions in our chat, but one of my questions would be getting to a more broader sense of regulation around all of this technology. So one of the biggest criticisms internationally when you go to ethics conferences around issues in reproduction, for example, if you sit at the Nuffield Center and talk with people there, is that the American approach to proceeding with these types of technologies is quote unquote the Wild West. And of course, our colleagues in our Department of REI would remind us that we have very aggressive regulatory requirements around how we produce and store and screen gametes and embryos. So it's not an accurate critique, yet on the other hand, we don't have the same level of oversight as they do, for example, through the HFEA at the UK. Just as a general principle, given your experience and the different committees you've served on over many decades, what's your thought on that? I remember, I've heard people say we like the freedom of less regulation in the US, and I've heard other people say we really struggle with the lack of guidance where all of our documents are guidelines only from the ASRM. Do you think there should be more stringent regulations in the development of these technologies? For example, polygenic scores and the like?
Yeah, well, I think the question is excellent, and I more likely would, if I had to write a paper about it, I would have to give it a lot of thought. I mean, the HFEA, for example, I never thought of as restrictive or illiberal. In many ways, the Europeans, who on the whole do not have a strong pro-life, in some ways you could say are quite liberal in their approaches. There was a time when Germany was deemed quite conservative. Post-World War II, I think there were residual concerns about going too far, maybe to this day. But if you look at liberal nations like Denmark and Holland, I don't really believe that they are in any way more conservative than we are. IVF, has been around now since 1981. Congress has taken steps to make sure that we keep careful tabs on how many cycles we do and the outcomes thereof. And that's where the CDC comes in. And that was Senator Wyden's bill back in 2012, I believe. Now, of course, he's a Democrat and a liberal Democrat at that. But we haven't seen any conservative moves since the one regulation that exists to this day, but hasn't been augmented or added to. Now, mind you, conservative or not, everybody wants to be a father and mother. And I remind you, for example, that Vice President Pence, for example, clearly a conservative, writes in his book that his 2 children were born by IVF. And clearly every conservative member of Congress must have observed closely or not so closely the application of therapy for infertility, including IVF. Everybody, or most everybody, at some point or another, runs into this issue. And in that respect, congressional Republican men and women are no different. And so my feeling always has been that in a final analysis, when it comes to reproduction, because we all, at some deep level, seek to be the parents of a child, or children. Whether we seek or whether it's our destiny, that's a separate discussion. But men and women don't marry just for the sake of an economic union. There's clearly an underlying hope and desire to establish a family. And whether you're a Democrat or a Republican is really immaterial. So I always felt that there was a line which conservatives will not cross because they too want to see their family thrive. And in the case of infertility, having it addressed. And all you need to do, as I say, is read Mike Pence's book, who makes it plain that his two children were born by IVF. And if we did a survey, if that were possible, of infertility in our Republican colleagues, particularly those in Congress or their relatives, and the degree to which they were exposed to fertility therapies and to IVF, I would predict that we will find quite a few examples of individuals who benefited from either fertility therapy or IVF in particular at some point. So I'm not too worried is what I'm trying to say. It's not going to be simple. And yes, I'm cognizant of the limitation. But still, I would say the future is bright,
Wonderful.
if I may say so.
I don't see any further questions in the room or on the chat. And so it's a great spot for us to end on. And I'll give people some time back in their mornings. Thank you so much for coming to speak with us. We're so grateful.
My pleasure.